Hello, curious minds. Have you ever wondered if there's a single unifying explanation for everything we see in the universe? From the vast expanse of galaxies to the tiniest particles, scientists are on a quest to discover a theory of everything that could unlock the secrets of our cosmos. In today's video, we'll dive into this cosmic puzzle and explore how one theory might connect it all. Buckle up for a journey through the most profound questions in science. So, what exactly is the theory of everything? In the simplest terms, it's a hypothetical framework that aims to unify all the fundamental forces of nature into one comprehensive theory. Imagine a single equation or a set of principles that could explain every force and every particle in the universe. Currently, we have four fundamental forces that govern everything we observe: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each of these forces operates in different realms, from the colossal scales of galaxies to the microscopic world of atoms and subatomic particles. Einstein's general relativity brilliantly explains gravity on the cosmic scale. On the other hand, quantum mechanics successfully describes the other three forces at the smallest scales. However, these two frameworks don't quite fit together, leaving a gap in our understanding. The theory of everything seeks to bridge this gap by uniting general relativity and quantum mechanics into a single, coherent framework. It's like finding the missing puzzle piece that completes the picture of how our universe operates. If successful, it would provide a complete and unified description of all physical aspects of reality. But why is this so significant? A theory of everything could not only explain the universe's workings from the smallest particles to the largest galaxies, but also reveal new insights into the nature of reality itself. It could lead to groundbreaking advances in technology, cosmology, and fundamental science. Now let's take a closer look at the four fundamental forces and how current theories attempt to describe them. First up, we have gravity, the force we're all familiar with. Gravity is the force that pulls objects toward each other. It's what keeps the planets in orbit around the sun and makes apples fall to the ground. Sir Isaac Newton first described gravity in the 17th century, but it was Albert Einstein's theory of general relativity that provided a deeper understanding. According to Einstein, gravity is the result of massive objects warping the fabric of space-time. In simpler terms, the more massive an object, the greater its gravitational pull. Gravity is the weakest of the four forces, but it has an infinite range and dominates on large scales, like in galaxies and across the universe. Next is electromagnetism. This force acts between electrically charged particles. It's responsible for electricity, magnetism, and light. If you've ever used a magnet or turned on a light switch, you've experienced electromagnetism in action. Electromagnetism can both attract and repel, depending on the charges involved. Unlike gravity, which only attracts, electromagnetism can create forces that push objects apart or pull them together. It's the second strongest force and has a much shorter range compared to gravity. Now let's dive into the heart of the atom, where we encounter the strong nuclear force. This is the force that holds the nuclei of atoms together. It's incredibly strong, about 100 times stronger than electromagnetism. But it only acts over very short distances within the nucleus of an atom. The strong nuclear force binds protons and neutrons together in the nucleus, overcoming the repulsive electromagnetic force between positively charged protons. Without this force, atomic nuclei wouldn't exist, and matter as we know it wouldn't hold together. Finally, we have the weak nuclear force. This force is responsible for radioactive decay and certain types of particle interactions. It's called weak because it's weaker than the strong nuclear force, but still crucial for processes like the decay of radioactive elements and the fusion reactions that power the sun. The weak nuclear force plays a key role in the life cycles of stars and the synthesis of elements in the universe. It has a very short range, even shorter than the strong nuclear force, and is mediated by W and Z bosons. Now let's dive into two of the most important theories in modern physics: general relativity and quantum mechanics. These theories describe how the universe operates on two very different scales, cosmic and microscopic. Let's explore each of them and see how they shape our understanding of reality. First, let's talk about general relativity. Developed by Albert Einstein in 1915, this theory revolutionized our understanding of gravity. Unlike the simple idea of gravity as a force pulling objects together, general relativity describes gravity as the warping of space-time caused by massive objects. According to general relativity, massive objects like stars and planets bend the fabric of space-time around them. This curvature affects the paths of other objects, causing them to orbit or move in ways that we perceive as gravitational attraction. It's this warping of space-time that causes the phenomena we observe as gravity. General relativity has been confirmed by many experiments and observations, including the bending of light around massive objects and the detection of gravitational waves. It's crucial for understanding the large-scale structure of the universe, from galaxies to black holes. Now, let's zoom into the microscopic world with quantum mechanics. Developed in the early 20th century, quantum mechanics deals with the behavior of particles at the smallest scales, atoms, and subatomic particles. Unlike classical physics, which describes objects in definite positions and velocities, quantum mechanics introduces a new level of uncertainty. In quantum mechanics, particles are described by wave functions that represent probabilities rather than definite positions. This means that we can only predict the likelihood of finding a particle in a certain place or state, not its exact location. This probabilistic nature is famously illustrated by Schrödinger's cat, a thought experiment where a cat is simultaneously both alive and dead until observed. Quantum mechanics also introduces the concept of quantum entanglement, where particles become linked in such a way that the state of one instantly affects the state of another, no matter the distance between them. These phenomena have been confirmed through numerous experiments and are foundational for modern technologies like quantum computing and cryptography. So, why are these theories important for the theory of everything? General relativity and quantum mechanics are incredibly successful in their own realms, cosmic and microscopic, but they don't seamlessly fit together. General relativity works well for large-scale phenomena like black holes and cosmic expansion, while quantum mechanics excels at explaining the behavior of particles at the smallest scales. The challenge is that general relativity describes gravity in terms of space-time curvature, while quantum mechanics describes forces in terms of probability and quantized states. Uniting these theories into a single framework that can describe both the vastness of space and the intricacies of the quantum world is one of the biggest challenges in modern physics. In summary, general relativity and quantum mechanics are two of the pillars of modern physics, each explaining different aspects of the universe. The quest to unify these theories into a single theory of everything is a key goal in theoretical physics and could unlock a deeper understanding of the universe. Up next, we'll explore some of the leading candidates for this unifying theory. Let's start with string theory. Imagine, if you will, the smallest constituents of the universe, not as point-like particles but as tiny vibrating strings of energy. These strings, far smaller than even the tiniest subatomic particle, are the fundamental building blocks of everything we see and experience. Just as a violin string can produce a variety of notes depending on its vibration, these cosmic strings vibrate at different frequencies, each frequency corresponding to a different type of particle. For example, they determine whether a string appears as an electron, quark, or photon. The entire universe in this elegant framework becomes an intricate symphony. What makes string theory so exciting is its potential to unify all four fundamental forces: gravity, electromagnetism, strong and weak nuclear forces, by describing them as different vibrations of strings. This could bridge the gap between general relativity and quantum mechanics, leading to a theory of everything. String theory also suggests that our universe has more dimensions, up to 10 or 11, beyond the familiar 3 dimensions of space and 1 of time. These extra dimensions are believed to be compactified or curled up so tightly that we don't perceive them in our everyday experience. However, it is important to note that string theory faces challenges. It's highly complex, difficult to test, and there are multiple versions of it, each describing a different universe. Moreover, direct experimental evidence is still lacking, making it a subject of ongoing debate in the scientific community. Loop quantum gravity, another fascinating contender in the quest for a theory of everything. Unlike string theory, loop quantum gravity reimagines the fabric of spacetime itself. Let's dive into how this theory works. Loop quantum gravity, or LQG, proposes that spacetime is not a smooth, continuous fabric, but is instead made up of tiny, discrete loops. Imagine spacetime as a woven fabric where each thread is a loop. These loops are incredibly small, about 10 circumflex 35 meters, the Planck length. These loops interconnect to form the very structure of spacetime. In LQG, gravity emerges from the way these loops are connected, rather than from the curvature of spacetime as in general relativity. This means that at the smallest scales, spacetime has a granular, quantized nature. One of the biggest challenges in physics is merging general relativity with quantum mechanics. Loop quantum gravity tackles this by quantizing spacetime itself, suggesting that even gravity can be understood in quantum terms. This could provide a framework where the laws of physics work consistently across all scales. LQG also offers new insights into extreme conditions, like inside black holes or at the moment of the Big Bang. Traditional physics breaks down at these singularities, but in LQG, the loops of spacetime could prevent the infinite densities that cause singularities, potentially leading to new theories about the birth of the universe and the nature of black holes. Despite its potential, loop quantum gravity faces challenges. It's still in development, and like string theory, it lacks direct experimental evidence. Some critics argue that it's too speculative or that it doesn't address all aspects of a unified theory. However, it remains a compelling approach to understanding the quantum nature of gravity. So far, we've journeyed through the well-trodden paths of string theory and loop quantum gravity, valiant attempts to mend the rift between the cosmic and the quantum. But the universe is a vast and mysterious ocean, and these are but two ships sailing its surface. There are other, perhaps less charted waters in theoretical physics where researchers seek the elusive theory of everything. One intriguing avenue is called the M-theory, an extension of string theory. While string theory describes particles as one-dimensional strings, M-theory introduces even more complexity by adding higher-dimensional objects called membranes or branes. This theory suggests that our universe might be just one of many, each existing on different branes within a higher-dimensional space. M-theory could provide a more complete framework for understanding the universe, but it's still highly theoretical and difficult to test. However, it's a fascinating possibility that expands the boundaries of string theory into new dimensions, literally. Beyond loop quantum gravity, there are several other approaches to understanding quantum gravity. Causal dynamical triangulations, CDT for example, models the universe's spacetime as a series of connected triangles evolving over time in a way that might reveal the quantum nature of gravity. Another approach, known as asymptotic safety, suggests that at extremely high energies, gravity might behave in a way that allows it to remain consistent with quantum mechanics. These approaches are still in early stages but offer unique insights into how gravity might work at quantum scales. Emergent gravity is another intriguing idea. Instead of treating gravity as a fundamental force, it suggests that gravity might actually emerge from more basic underlying principles, similar to how temperature emerges from the motion of molecules. This approach challenges our traditional view of gravity and could lead to new ways of understanding the cosmos. Emergent gravity is still a developing field, but it raises important questions about whether the forces we observe might be the result of deeper, more fundamental processes. Finally, there's the holographic principle, a mind-bending idea suggesting that our entire universe might be a projection of information encoded on a distant two-dimensional surface. This theory emerged from studies of black holes and has profound implications for our understanding of space, time, and reality itself. If true, the holographic principle could change how we think about everything, suggesting that our three-dimensional world is a kind of hologram, emerging from a more fundamental two-dimensional reality. Now let's get clear. Theories are just the beginning. What truly matters is evidence. Let's explore how scientists are searching for evidence to unlock the mysteries of the universe. One of the most powerful tools in the search for evidence is the particle collider, like the Large Hadron Collider, LHC, at CERN. By smashing particles together at nearly the speed of light, scientists can recreate conditions similar to those just after the Big Bang. These collisions might reveal new particles that could support or refute theories like string theory or loop quantum gravity. For example, the discovery of the Higgs boson in 2012 was a monumental step in confirming the standard model of particle physics. Now scientists are looking for even more exotic particles, like supersymmetric particles, which could provide crucial evidence for or against various unifying theories. Next, gravitational waves. They were first detected in 2015 by LIGO. They are ripples in the fabric of spacetime caused by violent cosmic events like colliding black holes. These waves offer a new way to study the universe and test theories like general relativity. But beyond that, they could also provide indirect evidence for theories of quantum gravity, as any deviations from predictions might hint at new physics. As detectors become more sensitive, we might observe phenomena that challenge our current understanding, pushing us closer to a theory of everything. The cosmic microwave background, or CMB, is the afterglow of the Big Bang and serves as a cosmic fingerprint of the early universe. By studying the tiny fluctuations in the CMB, scientists can test theories about the universe's birth and evolution. Any anomalies in the CMB data could provide evidence for ideas like extra dimensions or the multiverse. For example, if we detect patterns that align with predictions from string theory or M theory, it could be a breakthrough moment in our understanding of the cosmos. At the quantum level, scientists are conducting experiments that probe the very nature of spacetime. Quantum entanglement experiments, for instance, could reveal how spacetime is interconnected on a fundamental level, offering insights into theories like loop quantum gravity. These experiments are crucial because they could uncover new phenomena that challenge our current models, bringing us closer to a unified theory of physics. Now the real question, what happens if we actually find a theory of everything? It would provide a unified framework that explains all physical phenomena, from the smallest quantum particles to the vast structures of the cosmos. This would revolutionize our understanding of the universe, offering a complete picture of how everything works and how it all connects. Imagine being able to explain the birth of the universe, the behavior of black holes, and even the fundamental nature of time and space with a single coherent theory. This would not only solve many of the biggest mysteries in physics, but also reshape our view of reality. We could finally answer questions that have haunted humanity for millennia. The practical implications of a theory of everything could be just as transformative. Imagine harnessing the power of black holes or traveling through wormholes to distant corners of the cosmos. Of course, these are just some of the potential implications. The true beauty of a scientific breakthrough lies in its ability to unlock possibilities we haven't even dreamed of. Beyond the scientific and technological impacts, a theory of everything would have profound philosophical implications. It could answer some of humanity's oldest questions. Why does the universe exist? What is the nature of reality? Are there multiple universes? And what is our place in the cosmos? Such a discovery could challenge our understanding of free will, consciousness, and even the nature of existence itself. It might lead to new ways of thinking about life, purpose, and the universe's ultimate fate. Some might wonder if finding a theory of everything would mean the end of physics as we know it. After all, if we have a complete theory, what's left to discover? But in reality, such a theory might just be the beginning of a new era in science. It could raise new questions and open up entirely new fields of study, challenging us to explore even deeper levels of reality. Far from being the final chapter, a theory of everything could be the launchpad for the next great scientific revolution. We've embarked on a thrilling journey, haven't we? But the search for a theory of everything is far from over. Scientists around the world are pushing the boundaries of knowledge, armed with ever more sophisticated tools and ideas. From experiments at the Large Hadron Collider to deep space observations by the James Webb Space Telescope, every new piece of data could be the key to unlocking the universe's most profound mysteries. But the future may hold surprises. It's possible that in the pursuit of a theory of everything, we might discover entirely new paradigms that challenge our current theories. What if the universe is even stranger than we imagine, requiring a shift in our scientific worldview? The journey could redefine our understanding of reality itself. The road ahead is unpredictable, but that's what makes the quest so exciting. Every new discovery has the potential to reshape our view of the cosmos. And there you have it. We've explored the fascinating quest for the theory of everything, from its groundbreaking theories to the incredible implications it could have for our understanding of the universe. But the journey doesn't end here. Now, I'd love to hear from you. What do you think is the most exciting possibility of a theory of everything? Do you believe we'll ever find it, or are we still miles away? Drop your thoughts and theories in the comments below. Let's continue this conversation. If you enjoyed this deep dive into one of science's most exciting mysteries, don't forget to give this video a thumbs up, and subscribe for more cosmic adventures and thought-provoking content. Your support helps us continue to explore and explain the wonders of the universe. Thanks for watching. Until next time, keep looking up.